Integrated photonics, combining optics and electronics for faster communications. In today's world, communication is fundamental to our daily lives. Whether it's through the internet, mobile phones, or in person, the need to communicate with others is growing every day. The technology behind communication is rapidly evolving, and one exciting area of research is integrated photonics. This branch of science combines optics and electronics for the creation of faster and more reliable communication systems. Photonics is a relatively new field that explores optical communication, or the use of light to transmit information. It encompasses the use of lasers, optical fibers, and other related technologies. Electronics, on the other hand, involves the use of electrons to transmit and process information, such as the transistors that power the computer you're using to read this article. Integrated Photonics combines these two areas of science into a single platform to create faster and more efficient communication systems. One of the most significant advantages of integrated photonics is its speed. Photons, the fundamental components of light, are incredibly fast and are capable of transmitting data at high speeds. Current electronic communication systems use electrons, which are significantly slower than photons, leading to lag and delays in transmission. By combining optics and electronics, integrated photonics can create communication systems that are faster and more efficient than traditional electronic systems. Another significant advantage of integrated photonics is its reliability. Electronic communication systems rely on copper wire connections, which are prone to damage and interference. If the connections are disrupted or damaged in any way, communication will fail. On the other hand, integrated photonics use optical fibers, which are much less susceptible to damage and interference. This means communication systems using integrated photonics will be more reliable and less prone to failure. Integrated photonics is also cost-effective. Electronic systems require a significant amount of energy to operate, leading to higher power costs. Integrated photonics, however, uses less energy and generates less heat, making it less expensive to operate. Moreover, the use of silicon-based technologies allows for mass production of photonics devices, leading to lower costs and wider availability. Researchers have been exploring the possibilities of integrated photonics for several years now, and their work has culminated in the creation of many innovative products. For example, integrated photonics can be used to create high-speed data transmission systems for use in data centers. These systems can transmit large amounts of data over long distances, making them ideal for use in cloud computing. Another area where integrated photonics has shown great promise is in medical technology. Medical imaging devices such as MRI machines produce vast amounts of data that, until recently, had to be transmitted via copper wires. Integrated photonics-based devices can significantly speed up the data transmission process, making medical imaging devices faster and more efficient. Integrated photonics is also being explored for use in autonomous vehicles. Autonomous vehicles are equipped with numerous sensors that generate vast amounts of data. This data needs to be processed quickly and efficiently to make real-time decisions about the vehicle's movements and responses. Integrated photonics can provide the high-speed, reliable data processing that is necessary for autonomous vehicles to operate safely and efficiently. Despite the many advantages of integrated photonics, the technology is not without its challenges. One significant challenge is the need to integrate optics and electronics on a single platform. This requires the use of sophisticated manufacturing techniques to create devices that can optimize both optics and electronics. Another challenge is the need for better design tools to create integrated photonics devices. Finally, Researchers need to develop new materials to realize the full potential of integrated photonics. One exciting application of integrated photonics is in the field of quantum communication. Quantum communication uses the principles of quantum mechanics to transmit information securely, making it virtually impossible for hackers to intercept or decipher the information being transmitted. Integrated photonics can be used to create secure quantum communication systems by generating and detecting individual photons, which can encode and transmit information securely. Another potential application of integrated photonics is in the field of renewable energy. Solar cells that use integrated photonics can generate electricity using the energy from sunlight and transmit it to power grids in a more efficient, cost-effective, and reliable manner. This can potentially revolutionize the energy industry by providing a sustainable and eco-friendly alternative to traditional energy sources. Researchers are also exploring the use of integrated photonics in the field of sensing and imaging. Integrated photonics-based sensors can be used to detect specific gas molecules, bacteria, viruses, and other chemicals. This can be valuable in medical diagnosis, environmental monitoring, and industrial process control applications. In the field of imaging, integrated photonics-based cameras can generate high-resolution images with high sensitivity, low noise, and high dynamic range. This can be useful in many applications such as astronomy, microscopy, and surveillance. In addition to these applications, integrated photonics can also be used in the development of new computing systems. The future of integrated photonics looks very promising. Advances in materials, manufacturing techniques, and design tools will make it possible to create even more innovative and efficient tie-in systems. The widespread adoption of integrated photonics will lead to the development of new and exciting applications that will revolutionize many industries. Another application of integrated photonics is in the field of agriculture. The use of integrated photonic sensors can help farmers optimize the use of water, fertilizers, and pesticides, resulting in improved crop yields and reduced environmental impact. The sensors can detect the needs of crops in real time, allowing for timely interventions that help prevent crop damage or losses. Integrated photonics can also be used in the telecommunication industry. The development of 5 grams technology is paving the way for new communication systems that rely on integrated photonics. These EMS can provide faster and more reliable network speeds, enabling seamless connectivity across devices and platforms. The field of integrated photonics is also contributing to the development of smart cities. Cities around the world are becoming more connected and automated, and integrated photonics can support the development of the infrastructure needed for these changes. Integrated photonics-based sensors and networks can help monitor traffic, air quality, and energy consumption, and support the development of smart grids and energy-efficient buildings. Another exciting application of integrated photonics is in the field of quantum computing. Quantum computers use quantum bits or qubits to encode and process information. Integrated photonics-based technology can be used to generate and manipulate qubits, making it possible to develop highly efficient and powerful quantum computers. As integrated photonics technology continues to advance, it is expected to play an increasingly crucial role in many fields of science and technology. To achieve its full potential, integrated photonics requires collaboration between various disciplines, including physics, engineering, and computer science. This collaboration can help overcome the challenges associated with integrating optics and electronics and the development of new materials and design tools. The potential impact of integrated photonics is significant, and it is essential to appreciate the socioeconomic benefits it can provide. For instance, faster communication and data processing (SIST). MS can improve productivity and accelerate business growth, leading to job creation and increased market competitiveness. Similarly, integrated photonics-based devices can help increase the efficiency of medical procedures, reducing the time and cost of treatments. In addition, integrated photonics has the potential to reduce the digital divide that currently exists in many parts of the world. In remote or underdeveloped areas, traditional communication infrastructure may be limited, making it difficult to access essential services such as healthcare, education, or business opportunities. Integrated photonics-based communication systems can help bridge this gap by providing high-speed and reliable access to information and services. Moreover, integrated photonics can play a vital role in achieving sustainability goals and reducing the carbon footprint of many industries. For example, the use of integrated photonic sensors can